Welcome to example number 4. We have a long spring attached to a wall. Here's my wall, and here's my spring, and it's 20 centimeters long. And then we pull it horizontally with a force of 100 newtons, and it stretches to a new position of 22 centimeters. And so it stretches 22 centimeters when this force, F, is pulling on it with a force of 100 newtons. So the same spring is now connected to a hook and 10.2 kilogram block that is attached to the bottom end, and we want to know how long is the stretch spring. So the first thing I'll do before I tackle this part with a 10.2 kilogram block is I can get some information from this picture. You see, I'm going to assume that this spring here is the same spring that we used with the 10.2 kilogram block, right? So, and the one thing that doesn't change for the spring is the spring constant. So let's go ahead and try to find that spring constant. If you remember, let's use the AP version. The magnitude of the spring force is equal to K times the magnitude of the stretch distance. So the magnitude of the spring force would be equal to, say, 100 newtons, and K. And then the magnitude of the stretch distance, the displacement, in this case would be, well, 22 minus 20. That would be basically 2 centimeters, which is 0.02 meters. So therefore, we've just established that the spring constant is equal to 5,000 newtons per meter. So now let's take a look at this scenario with a 10.2 kilogram block attached to the bottom end of it. So now the spring is vertically oriented, now attached with this block that has a mass of 10.2 kilograms. All right, so what I would do is draw a free body diagram for the block. So if we consider this dot the block, and if you were to consider yourself the block, what forces would be acting on you externally? Well, you would feel a spring pulling you upwards, and then you would feel the force of gravity pulling you downwards. We'll label that as F sub S, and label this one as F sub G. And so we know that these two forces must be equal to each other because the sum of the forces must balance out to be 0 vertically. So the spring force must be equal to the force of gravity. And we could calculate the force of gravity because we know that's equal to m times g. So the spring force is m times g, and m is 10.2 kilograms, and g is 9.8 newtons per kilogram. That gives us a force of 99.96 newtons. So now that we know the spring force, and we also know the K, then we can find the new extension. So moving on from here, let's use the same formula. The spring force is equal to K times the stretch distance. The spring force is now 99.96 newtons. K is still the same spring, so it's 5,000 newtons per meter, and so we can find the new stretch distance x. So the stretch distance will be equal to 0.019992 meters. But that's not the answers that's listed down below if you look carefully. So why is that so? Well, this is technically, let's round that off to 0.02 meters, or essentially 2 centimeters. And you notice it's 22 centimeters. What did we forget to include? See, we're not looking at the stretch distance. We're looking at how long the entire spring is. Remember, the spring was originally 20 centimeters. So the actual length of the spring is really 20 centimeters plus this extra stretch distance of 2 centimeters. So that gives you a total length of the spring now of 22 centimeters. Which is kind of funny. You know, I went through all that rigmarole and I'm realizing that, hey, if I applied roughly 100 newtons, then isn't it the same thing? If I apply it vertically, the same thing as horizontally? So really, after doing all that math, I could have just said, well, I'm applying the same force, so it's just going to stretch to the same original distance that it was, which is 22 centimeters. Yep, that's it.